So my name is Kris Van Hees. I work for Oracle. I've been working for a bit over 20 years now, primarily in languages and tools. I've been working with debuggers, with GCC, and in the past 8 to 9 years, primarily been focusing on tracing and DTrace in specific. And I should probably add here already that in terms of DTrace and Linux, about 8 years ago is when I was asked by some people in upper management that, hey, we would like to have DTrace on Linux. And so that question came to me as the more senior person in this, and my response was, not going to happen. You know, it's not likely that it's going to be possible the way it's written for Solaris. Linux is different. And so the response was, well, do it anyway. So that's why we've been working on it, and it's been an interesting scenario. So just a little bit of an overview of DTrace itself. Not everybody knows what all its components are. I primarily put this up as a graphic so that I can show where we're going from this. So DTrace was designed as a complete system of fairly large kernel component and a user space component on top of that. And they have a very close interaction with each other, which was a good design, but it's not really working that well going forward, and that's why we're starting to make changes. So it really is top to bottom. So there's the user space consumer, just uses all the data, interacts with the kernel, but it's really a front end for the whole kernel portion. Essentially, anything below user space consumer sits in the kernel. So that's a very large chunk of code, and it's pretty invasive. But it does its own buffer management. It has its own execution engine. And then on the bottom, we have all the probes, which are also being provided by specific modules that are part of DTrace. So in a way, it was a nice design because we could just say, okay, we have here this patch, and right now we can take regular upstream kernel, apply the patch to it, resolve some merge conflicts, and you have DTrace in your kernel. And whatever else happens with K probes or whatever, ultimately doesn't affect us because we're not really using it, which is nice in a way and really, really, really bad in other ways. So that's what we're trying to get away from. So again, from the user space perspective, all your probing is working from a concept of 3 different contexts, and that's really tracing context. So we have the probe context, which means that we have access to registers, we have access to arguments to functions, return values, depending on which probes. We have access to all information about tasks. Pretty much anything that's in the task struct or is referenced from it, we should be able to have access to. And then there's also the consumer context, which is the actual buffering. There's aggregations, there is speculative tracing that has its own buffer. So that is all concepts within user space. And then, as I mentioned, everything else is kernel and kernel modules. So specifically at the kernel level, and built into the kernel tree, is starting to find tracing probes, similar to the trace points that exist, but DTrace had as one of its features, ultimately, a set collection of probes that exist on every single operating system where DTrace exists, and it passes the same arguments with the probe, so it's very nice that you can write a script that will work on different OSs if you're going to do this kind of a high-level tracing. But it means we need to have those probes. So those have been added. We have our own probing mechanisms, probe firing, which, as I mentioned, is less than ideal given the fact that duplicating what already exists. We have our own task management. There's certain things that we need to do when tasks are created and tasks exit that we need to be able to tap into. So there's code for that. And then certain, at least kernel features that we have added need to be exported as part of the API. We have quite a few functions there so that our kernel modules can use them. So I'm not quite proud of this design, but this is the design of DTrace as it has been handed down from the beginning. And so in order to be able to implement this is what we had to do. And so then we have the kernel modules, which is one core module that does pretty much all the heavy lifting of doing the actual tracing work. It's the interface to the providers that give you information about probes. It executes actions when probes fire. It does buffer management, all that. And then a whole bunch of smaller modules that simply provides probes in their own version, because let's say a static probe will pass its arguments in a certain way. A user space probe will have arguments in a different way, so this kind of hides that and has a consistent API to be used by the DTrace core, so that you can write your scripts accessing the arguments of the probe and how you get those is encoded in the provider modules. So that has worked really, really well for a very long time. But the problem is that anytime there's a kernel change somewhere, we need to make adjustments. And we've been very happy to see that there have been many very positive changes in the kernel. But we have to adjust to that. We have to work around that sometimes. Things suddenly get moved around, especially when the task struct has a very tiny small change that has major effects. So it's been a bit of a nightmare to keep that going. So then we started looking at eBPF, because one of the things we saw is that this very big thing in the middle of the first graph I showed is this execution engine. We have something that executes some kind of a bytecode, and there is eBPF. Why should we maintain our own if there's something that already exists? So we started looking at that, and it is designed to be safe and fast, which is what we've been working on our side, and sometimes having to fix some issues with. Does just-in-time compilation, which is something that DTrace has never done, and the way it's designed, it's useless, because the snippets of code that are being executed in existing, what I would call now legacy DTrace, is so small that there's no point. So that's something that we could benefit from. And since you can attach it to probes, they started to develop a bit of a vision. And I started looking at the original chart that I made and started, well, if I can replace that by using eBPF and they attach to the probes, well, and I can get rid of this part and that part, and I started scratching out a whole bunch of things. And this picture started to look really, really pretty. So we started looking deeper into so what tracing facilities do we have in the kernel? And we obviously were aware of them, but we've been out of necessity ignoring them, which is not a nice thing to do. But there was no way to tap them in together without doing a major change in DTrace, which is essentially what we're doing now. But I guess we didn't have really that going for us yet. So what we have in DTrace, which is the static defined probes, trace points are pretty much the same thing. So we started looking at which trace points can we use to provide the same static probes. And if we can't, can we maybe suggest adding some more trace points that would fit what we need. Function boundary tracing. You have kprobe, you have krect probe. Same thing. It's entry into a kernel function, return from a kernel function. We can use this, and there are reasons why we didn't, and these reasons still exist, and I'll get to that on a few later slides. We have this thing called a PIT provider, which is essentially just user space probing. It's kind of user space function boundary probe in many ways, where you can also do arbitrary addresses. That's uprobes. And in fact, in the current implementation of DTrace with the very invasive kernel patch, that's the one part I'm really proud of. It uses uprobes. So that was a very easy one to implement. The profile provider, software timer events, well, they exist. Might as well use them. And for system calls, there are trace points that give you entry and exit. And that's the area that has changed the most in the years that I've been working with DTrace. And it's been nice to see that it has been changing in the direction that makes it so much easier for us to tap into it. So we started out with essentially replacing the function pointers for the system calls in the system call table. And that way kind of tapping into the flow. And now it's being done for us. And so instead of adjusting to that over and over and over again and slowly merging towards maybe what seems to be more clean, we kind of left that by the wayside for a while, and now we're going to really do the major switchover. So since all these tracing events are exposed through a sysfs, they're all presented as the same kind of tracing events. eBPF programs can be attached to all of them. It stands to reason that we kind of have this lower level of probes. We have this concept of providers that's given a common API to the execution engine. Well, this has been done for us. But again, we can really start using this, and that kind of became a mantra over and over on our weekly conference calls. That we really started to, almost to the point of getting nauseated by it, commenting on the fact that we should just use what's there. And that's where we're getting to. So when you trace with eBPF, and that's something I needed to look at because DTrace had its own way of doing things. Like I mentioned, it was this whole system of tracing that just you can really plug into the kernel in many ways, but it's by itself. It does its job, but it doesn't really interact much with anything else but then just the system. So we need to look at how BPF does things. And so you can create a probe, or you can open the perf event, because creating a K probe or U probe simply provide us with a matching perf event that then we can tap into. You load the eBPF program, attach it. Most probes are created, enabled already, so you don't even have to do that part. Generate output using some BPF helper functions, and that's pretty much it. Yeah, it's very straightforward, as I mentioned. And the eBPF programs can be compiled with C-line LLVM. And that was kind of the portion that started making it a little more tricky for us, since we, for various reasons, do not have access to C-line LLVM on most of the systems where we need to use DTrace. And just compiling data statically linked was not really an option. Plus, DTrace uses its own scripting languages similar to C, but not quite C, that it wasn't that practical. So the straightforwardness became, as we started looking deeper, a little bit less. And then we started digging into other complications that were coming up. And in many ways, this was me playing devil's advocate within our team, which led to fascinating discussions, because I was also the one leading the effort to do this change, and then arguing against it at the same time, and see what they would come up with. And so I uncovered a couple of things that we foresee are going to be a headache, but we hope we're going to be able to work through. One of the things is that BPF programs generally are small, but every program that's loaded takes up a memory page. And that's where I started getting very nervous, because a lot of tracing scenarios that we have looked at from various other teams and projects do fairly short-term, very specific tracing. Now, we have some use cases that we have been working with where you're tracing 20, 30,000 probes. Now, we find dedicating 20 to 30,000 memory pages on just the BPF programs, that's an issue. And you can't share them between different types and stuff. So that's not resolved. And you're going to see a couple of other slides where I think I'm indicating the fact that we're shoving this to the side and hope that somehow we fix this or somebody else will. But we don't want this to stop us. There is also the fact that all the probe types that exist, so they're grouped in types. You have the K probes, you have the trace points, you have the raw trace points, you have this whole collection. They all have their own context in which they operate, which is essentially the kind of information that is passed with them when the eBPF program is called. And you can't switch from one to the other. So instead of having this beautiful concept of everything is a trace event, we do have that, but all these different similarly looking trace events are executing BPF code in totally different contexts with their own functions and helper functions that they have available. So I can't count on the fact that, a trace event fires, I know how I can use it. And the problem is that the BPF program itself doesn't know under which program type is running. So even if I write one and attach it to 3 different program types, they can't run the same way, because I might try to call a helper that doesn't exist in one of them. Again, things I just decide to ignore. We'll deal with that at some point in life. BPF doesn't allow dereferencing pointers, although there are helper functions that can get us around that. But we had to start thinking about how do we make this work. And so then we went back to DTrace, and this is extremely embarrassing to admit, but this is kind of the point, and now we're talking somewhere early last year. I started looking at what documentation exists for DTrace, what technical documentation exists, and realized that we don't really actually have a very well written up design of how DTrace was designed back in early 2000s. So we started analyzing how does it actually work. Like, I know how it works technically, but if I need to explain it to somebody, it's not that easy. And so we started looking at the phytoplates. So D programs are being compiled into diff code. All the probe types trigger execution in the same context, and that was like a big thing. That made me lose a lot of hope. We don't have these different probe-specific contexts. As far as DTrace is concerned, the moment the probe fires and it leaves essentially the main handler that calls into the DTrace core, every probe is the same. They all pass arguments. I want to have the argument, it calls a callback function, even provided it will give me the value, but I can treat every single probe the same way. Here I could not do that. The way that data was being passed back to user space, DTrace has its own buffering system. We didn't really want to say, okay, we're going to start using everything that exists in the kernel, but we're going to add our own buffering system again. Because we start replacing things again. But how could we marry the two without having to rewrite user space? Because the goal was not to start writing DTrace from the ground up again. And then the naming of probes, which seems like a very silly thing to talk about, but it's kind of important in DTrace that you can name probes a certain way. So if we look at the workflow, and I'm going to go through this very quickly, and if it seems confusing, it is. And just, it's the reality I've had to live with for many years of my life now. So a D-script is a collection of classes tied to one or more probes. So you specify a probe, possibly with wildcards or a list of probes, and then a piece of code, and then some more probes. Most scripts usually involve quite a few probes. Then each of those classes is considered a sequence of actions. Now it's written as a block of code that looks like a function in C. And that is how I, for a very long time, interpreted it until I started looking at this. And then I realized, oh, that's not what it is. And that made life, again, complicated. It's compiled into actions. It looks at, what is a statement that generates data? What is a statement that manipulates variables? What statements call functions? What statements do aggregation? And each of those statements separately is considered an action. And then those actions might have some code associated with them. And so what really happens is that you have this script that looks like a bunch of C-style functions, and in reality this is a very complex tree of classes with actions, and each action may have a snippet of code that is being compiled into this diff code, the intermediate format. And so when a probe fires, there is like in this big execution engine, this main module, there's this big loop that goes over all the classes, all the actions, and if action has some diff code associated with it that is hands off to an emulator that runs it, takes the results, and sticks it somewhere. And that's the moment I realized this doesn't work with eBPF. eBPF, the probe executes BPF code, and the BPF code does something, but you can't go from there into C code and then back into eBPF code or mix these things. It absolutely doesn't work. So this model was not possible. So the first attempt we made, well, I should say I made, I should take responsibility for this failure, was basically we were going to redesign it, BPF, we're going to use eBPF, we're going to use the kernel features. I did a very lengthy analysis of what is available in the kernel, how can we use it, what is missing, kind of using software engineering at its best. And I came up with the idea, okay, so these are the things that are missing, let's propose those as patches to the kernel. That was not well received. It was, okay, so why do you want these patches? Well, we need them. Why do we need them? Well, because we looked at DTrace and DTrace needs these. We don't think you need them. And there's no proof that we can give that says, well, no, we really need this. We can't do this any other way. So that was sunk very, very quickly with some positive comments and some less positive comments, but they all boiled down to, don't do this. So we had to abandon that. So with some help from some kernel developers who were explaining this is not how you do things in the kernel. And I've done things before in the kernel, but not of this magnitude, and many years ago before things become more complicated. So we were set on using this in a very incremental way. And that makes sense. And I decided to do that, and I decided, you know what, we're going about this the wrong way. You know, if we want to be part of the whole tracing infrastructure on Linux, we really should try to do this outside of the kernel. Use what is in the kernel and kind of do what we were given as feedback in sometimes not the most pleasant ways from the kernel developers. Show us you need this before we add something, or show that something doesn't work. So we took the philosophy, let's just assume this works. We can do these no kernel modifications. We're going to be able to DTrace 1% of the user space. I can guarantee you, I knew from the very moment I said that, not gonna happen. But it's the way we need to approach this. And so that's what we're doing. We assume we can do this. And we can assume we can do this in a way that the performance that we've grown accustomed to with DTrace, the stability, all will be maintained. We do this, we try it. If we fail, well, then we know what areas we need to fix. And so that's the process we've been working on. So before I go on this, and I deliberately put this kind of late in the presentation, because I want to show what we're doing, where we're coming from, but why do we bother? And that's a question I've been asked, I know, way too many times in the past 12 months. Why do we care? Why do we bother making DTrace work on top of eBPF, on top of other tracing facilities when there's other tracers around? There's so many projects. And the main reason is that, and I should start with kind of the third point, people want it. We've been told by quite a few of our customers, internal teams, people that like DTrace, that they want DTrace. And our approach is, well, then why not? And the reason why they like DTrace or want it is because they're familiar with it. It's a very well documented, it's a mature system, and that's why it's so important that we implement what has been documented, what people have come to expect, and not sacrifice on that. And it exists for multiple OSs, so again, people are familiar, people can use similar scripts in very easy ways, and it's very powerful as a programmable tracing system. You can literally trace from user space all the way down to the lowest level of the kernel and associate those events with each other, so really see what's going on. And the point that I put on the very bottom that I put aside is actually my favorite one in this, is that I like DTrace. I've grown to like DTrace, I should say. But it has limitations in its design because of how it originally was designed. So we wanted to be able to change it. We want to be able to move it forward. Like it doesn't have conditionals. Well, you know what? That's kind of crazy. In this day and age, anything that's scripted should have conditionals. We can do that if we move on to eBPF. So the design is literally going to be the very top. The user space is what is DTrace. Everything below it is currently already in the kernel, existing features in the kernel. Like I said, I think some people are going to have to get some contributions, but that is the general idea. So instead of doing this whole complex thing with clauses, we're just going to generate eBPF programs. And we're doing typically two. One is a trampoline from the probe that sets up what is similar to a context and then calls the actual eBPF program for DTrace. That means we have a consistent set of data that we can work with. And then we just attach to the probe and do typical probing. If we find issues, it means we're working with existing code, and we can flag that, we can work out solutions. DTrace has its own compiler. It has its own scripting language, its own compiler, so we have full control over that. It makes things a lot easier. But it also now means that by moving everything to user space, the user space component is going to define everything that's going to get done. Like if things happen on the kernel, it's not going to affect user space directly. And it's a very big shift for DTrace. It's never been that way. It always expected to have the control in the kernel. Now the control is on the user space level. And again, the biggest advantage from my perspective is that we don't have to maintain everything. If certain form of probing doesn't work, well, we can let somebody know who wrote it. So we have 2 contributions already lined up for the kernel because they simply do not exist. And I have to apologize. Apparently CTF is like an acronym that gets used all over the place. So Microsystems came up with this one for the compact C-type format, so we're stuck with it. So that is one thing that is already being added. In the last slide I've listed. GCC can generate it, BDTools has support for it. So that gives us type data for the kernel and a variant of the KAllSIMS information where we know whether a certain function exists in a kernel module, whether it's compiled in or not, is important for the consistent naming. So there's a whole bunch of mysteries, like I said, that we need to still resolve. Whether existing probes are sufficient, what we do in case they are not, if we should do translation, and like there's a whole list of unknowns, but we're proceeding as if they're resolved, and as we hit one, we're going to find a way to resolve them, and worst case, do it with kernel contributions. So currently, this whole project, and Jose Marchesi and Nick Alcom have worked on this a lot as well. Currently, as far as the tool chain, we have compiler support for eBPF. Is being added to GCCs. The patches have been posted. So that's as an alternative to LLVM, and it just makes sense. There's tools chain support for eBPF. The compact C-type formats has been added to BNutils, and GCC can work with that as well. We're using eBPF right now, which is part of that in the kernel source. But that is probably something we're going to not use anymore very soon because we have our own way of featuring to do that. And then the last link is where the current work that we found as a 2.0 branch for DTrace of the user space that is rapidly changing. Like I'm on a daily basis, I'm working with it. But that is kind of the work in progress as it's moving forward. Right now, it cannot probe. It can show you the probes, it cannot probe itself. It can compile programs, it can't load them. But again, this is changing on a daily basis. But it kind of gives you a view of where things are heading. And as we get the first probing, I'm sure we'll announce that very quickly. So, that is it.
Thank you very much. Are there any questions? So there's one thing I'd really like to see. So there's really those 2 main approaches for tracing. One is kind of live aggregation within the kernel, and other tools take the route of doing post-processing analysis with buffering. So one thing I see could have some value there would be to basically allow the DTrace language to be used to express both live aggregation types of analysis as well as being integrated with more post-processing approach. So you could basically run that on buffered traces.
Yeah, and in many ways it's kind of part of how DTrace has been designed. And that is one component that actually we still want to make some changes to if possible, which is that currently the user space part was designed to separate the visualization of the data from the actual getting it from the kernel to do the buffer management. And somewhere I can only assume that when originally this was designed and written, that was part of the design and then they kind of abandoned it for most likely time constraints. And so that is something that we would like to do again, and there is some code in there, it just never finished, that yes, we can get the data out and then present it to another backend that might want to use it. So where the DTrace, instead of that being your user interface, it is more the user space component that does the tracing, provides the data, and then can indeed a higher level tool to use it. And that definitely is part of the plans, because we would not want the DTrace user space to again kind of now become the new kernel where everything is in one single entity. So yeah, that's definitely will keep in mind.
Thank you for the talk. There is already a project called as BPF Trace, where the scripts look very, very close to the DTrace scripts. And will there be an opportunity to not use the DTrace compiler, but actually transpile DTrace scripts to BPF Trace, which then can become...
That would be more of a question for the people behind eBPF Trace. So I don't have any control over that. It has been suggested that might be an option. But last I looked, eBPF Trace does not quite have the feature sets that DTrace provides. And so and again, one of the big points behind doing this was that we need to provide DTrace, not something that's close to DTrace, not something that is like DTrace, but literally DTrace. And it should be in a way where people can take their scripts that they currently use in, let's call it version 1 of DTrace, and run them with version 2. And they should not have to change anything. And it should just work. And I mean, that part I can pretty much guarantee will work. Things about performance, things about stabilities, obviously needs to be worked out, and we need to see how we do that, but that guarantee needs to be there. DTrace needs to be DTrace.
Okay. Thanks for your work.
No problem.
Any other questions? All right, so thank you very much.